As mentioned, I am coming from the area of infrastructure, and I'm the director of something called the Centre for Smart Infrastructure and Construction. Just to clarify what I mean by infrastructure, in our centre we mainly deal with the big linear infrastructures. So that's railways, roads, water provision, wastewater treatment, power, ICT systems, that sort of thing. So it's the big infrastructure that is, if you like, the kind of the arteries of our cities and between our cities. I must also make it very clear that I am in no way a data scientist. However, the area in which we work has a number of data science challenges which I will endeavour to describe to you. If we get into any questions later where difficult data science things emerge, I will be referring you to my colleague Krishna, who's come with me today, who knows the data science bits of this very well. So just to sort of talk a little bit about the context and why any of this is important. As I mentioned, our infrastructure is really the lifeline of our cities. It's what keeps our cities moving. And it's facing a number of significant challenges. Our infrastructure is ageing, particularly in the more developed, or the longer developed world, if you like, where we had the Industrial Revolution 200 years ago. A lot of our infrastructure is 200 or more years old. In the UK, a lot of our transport infrastructure was built in the mid to late 19th century, so it's really struggling. It's in a very uncertain condition, and the picture on the top right there was the Twin Cities bridge collapse, which happened in the rush hour. Sadly, it caused loss of life. It also caused a lot of economic disruption, because one of the main arteries between the two cities on either side of that river was severed for quite a long time. It's being loaded ever more heavily. I won't explain that graph down the bottom, but essentially we're expecting more and more out of this ageing infrastructure that's in uncertain condition. And in addition to that, it's having to face challenges like climate change. So we're really at a sort of a nexus of challenge here. And all of that has implications for how we design our infrastructure, how we operate it, how we maintain it, and how we keep it safe. So all of that is vital. Now into that, The Economist back in 2010 did an article on superstructures and adding sensors into them. And they posed the very sensible question that if a car can be made smart enough to know when the oil is low or a brake light has failed, why can't we do the same for bridges, tunnels and buildings? Obviously, if it was a simple challenge, people would have done it before. It's not a simple challenge, but it's a very good question. And that's the area that our centre operates in. And we work with 40 industry partners because our industry is very fragmented. And so actually, one of our big challenges is that no one owns the whole of the problem, and certainly no one owns the whole of the data. The great opportunity that presents itself now is that with the kind of rush of development in sensor technology, ICT technology, and so forth, there's a real opportunity to start to sensor up our systems and ensure that we have resilient infrastructure going into the future. So in CSIC, we divide this problem into 4 main categories. Starting at the bottom of this sort of pyramid, we have sensors and data collection. As has been mentioned several times before, you need to have good data for any of this to work, or at least you need to know how bad your data is. So that's one of the areas that we look at. And one of our challenges is we work in a very chaotic environment. We're working outdoors a lot of the time. It's an environment in which the public operates a lot, so things are very unpredictable in terms of how our data is being gathered. Once you've got the data, you've got to analyse and interpret it, and that's really the main area that we're all looking at today. And once you've analysed and interpreted it, you need to use it to make decisions, as Professor Cheng said just now. And the sort of decisions we're looking at are how do we manage our assets? Now again, one of the big challenges we have in our realm is that our assets are very long-lived. We might be managing assets that have been around for 100 years, or we might be building assets which might be expected to be around for another 100 years. So we've got an extremely long time frame that we need to gather data over and understand that data. And we're at the beginning of this sort of data revolution. And I think one of the more unique things about infrastructure is that we've really got to think about the long life of this data for every single structure that we build. And then beyond that, we've then got to link it all together to the bigger city, to the other infrastructure systems, because all of our infrastructure is interdependent. And that just is sort of highlighted here. So if we start on the left with our cities and our infrastructure systems, they have performance requirements of our assets. To manage our assets, we need information, which is provided through data analysis and interpretation, but you can only do that if you've got the data. And then feeding back the other way, we gather the data with our sensors, we analyse and interpret it to provide that information and enable the decision-making that will enable our cities to continue to run in the way they need to. Very briefly, what might that look like? Those of you who go through London much or have watched some very good BBC documentaries will know that Crossrail is being built across London at the moment. They're building 42 kilometres of tunnel. This is a vision of what Crossrail 2 or maybe Crossrail 3 might be able to achieve. So you've got a tunnel boring machine coming across the middle of this picture, and on the top right-hand side, you've got a building with these big piles which support most of the big buildings in London. And those piles have been instrumented in this future world, and they're reporting that they're fine. The boring machine hasn't clipped the piles. That happens more often than you'd like to think. and everything's okay here. The boring machine's just gone over a sewer, the bottom right-hand side there, and the sewer's saying, yes, I'm instrumented, I think I'm fine, but you just might want to come and check because I'm a piece of critical national infrastructure. And then it's heading towards a London Underground tunnel, and the London Underground tunnels, they worry a lot about clearances because they've made the trains as big as they can within the tunnels. So if the tunnel starts to sag, then they worry about, impact. So they're reporting back, hang on a minute, slow down guys, we're starting to see some movement here that we're not happy with, we need to address that before you go any further. There's a lot of challenges in this. You've got to have the right sensors, they've got to be able to report their data, you've got to be able to gather it together, and you've got a lot of different organisations involved in just that picture. So this sort of starts to give you a picture of some of what we're looking at. I'm going to skip the next slide. The other thing is that whilst we call ourselves the Centre for Smart Infrastructure, and a lot of us are civil engineers, obviously we lean heavily on a number of other areas. And apart from perhaps the high-value manufacturing, all of those other areas are things that we sort of touch on in discussions about big data. Pervasive sensing, Internet of Things, enabling us to generate these quantities of data. And then BIM, smart cities, and the open data, they're really all about sort of standards and how we interface that stuff, which is challenging. So our centre has instrumented a huge amount of infrastructure, and a number of our industry partners are starting to do this for real in industry as well. So we're starting to generate some volumes of data. And the important thing is we use a whole range of different sensors to do this. Some of them are individual point sensors that we stick on things. Some of them are fibre optic, so it's a bit like having a long piece of string that you drape over your structure. It's a 2D thing in a 3D space. Some of them are monitoring and measuring how people are moving around a space. Some of them are using mobile phone sensors. There's a whole range of things we can do to gather data, and it's all different types of data. And that's used at all elements of the life cycle of our structures. So from design to construction to operation to maintenance and to replacement. And if you just take one of those elements there and think about the construction of an asset, there's a number of different things you want to achieve through monitoring. A lot of people don't often ask the question of why are we monitoring in the first place. So one of the challenges we're working with industry is about, what kind of data do you want to gather and how and why and what are you going to use it for? And it could be used for understanding how your construction process is going, to keep people safe. It can be used for managing risks, legal records, etc., etc. So there's a whole range of reasons why you might want to gather the data just for the construction part of the life cycle. And if you're gathering that data, there's all sorts of different kinds of data that you might need. You might need physical movement, you might need to understand pressures, you might need to be able to log the progress of the construction. So for example, where is that tunnel boring machine at any point in time? You might be wanting to measure temperature, you might need to know about the weather, all sorts of stuff you need to be measuring just to control your construction process. And if we just look at the movements piece of that, then there's a whole range of ways that we can gather that data as well. And we might be using all of those on any given site. So just for one small element of that bigger picture, we've got a vast way of gathering that information. So our main challenge, if you think about the kind of the V's of big data, really is variety. And that variety is, if you like, a physical variety, so position. Are we measuring position in 1 dimension, 2 dimensions, 3 dimensions with scans? Location, which is a different thing. Where is that sensor? The temperature, the humidity. We might be measuring acceleration to monitor movements. We might be storing images to either calculate differential movement or to look for changes in a structure or for any number of things. But it's not just about the physical variety of what we're measuring. It's also about the time variety. Because we have assets which last for hundreds of years, we might be measuring some things, for example, on a construction site, many times a second. If you're looking at the stability of a wall where you're digging a trench, you need to know immediately if there's something going to happen with that and it's going to collapse. On the other hand, some sensors, you might be happy that they report once a minute, once a week, once a month, or even once a year, when you're looking at things that are going to be changing over the long lifetime of that asset. So we've got variety in two kind of different axes. We also have the challenge of veracity, both is what I'm gathering right now true, or have I got some faulty sensors in the field? But also over time. So as we get more and more distant from the point in time at which that data was gathered, how much faith do we have in it now? And that could be caused by loss of information about how that data was gathered, or it could be caused by, for example, we've gathered that data and interpreted it using one system, and we now know 10 years later that there's a better way of interpreting that data. If we can get back to the original data, then we can reinterpret it and we have good data. If we can't get back to the original data, then we have to live with the fact that that data's quality has degraded. And then finally, we use it for different purposes. So there's the responsive purpose in terms of I'm monitoring things on my construction site, or I'm operating my railway and I need to make sure that things are flowing appropriately. There's, if you like, what I call the reflective purpose. So we're still in this sort of dynamic mode, but what can I learn from last week's operation or the previous piling operation that I did in construction to improve the next time I do that? And then there's the much longer term piece, which is what condition is my asset in and how much longer can I operate it for example, before I need to go in and maintain it. So we're cutting that time axis in different ways for different purposes. The other challenge that we have, because we're in an immature world in this science, is data standards. There's a number of different data standards that affect us directly. There's the Smart Cities standard, which some of you may have come across. PAS 180 and PAS 182, don't quite know how I type that. There's asset management standards, which also look at data. And there's the BIM standard. So BIM stands for Building Information Modelling. And that is essentially a way of, in theory, a way of making sure that from the very beginning of the life cycle of an asset, when it's an idea in someone's head, all the way through to the point you might want to decommission it, all that data about the design decisions, the maintenance decisions, etc., can be hung off this building information model. It's definitely an emerging area, but it potentially is very significant and will enable us to do fantastic things with our assets. We need to make sure that all of these line up, because if we don't, then the people running our assets are going to be in a bit of a spin and aren't really going to know how to cope with this. Because if you think about Transport for London, they are enabling a city, they are building buildings, they're running assets, and they need all of those data standards to be pointing in the same direction. Otherwise, they're not going to be able to achieve what they need to do. Brief note on smart city standards. So we started a project recently at one of our sites, London Bridge, where we thought, well, let's explore this smart city stuff, because smart city standards were originally conceived to enable cities to share all kinds of data, and a lot of that may be sort of social data. We often hear sad stories about, for example, children who've died, and all of the information that would have alerted people to the fact that there was a problem in that family existed, but it wasn't hooked up. So one of the things that Smart City Standards want to do is enable all those different agencies to share data about an individual based on, who that individual is, or where they live, or where they go to school, or who else might live near them, etc., so that you don't miss things like that. But that is obviously a very different challenge to the pointy engineering challenge of how's my construction process going. So we wanted to look at this smart city standard system and say, can we apply it to our data? Now, one of the slight challenges with it is that it aims to seamlessly integrate the information from multiple organisations using semantic web technology, and this is where I'm bordering on the edges of my knowledge. That is a very, very good system if you want to browse data. It's not a very good system, I'm told by my data science colleagues, if you want to dive in and start to analyse things and come at things from all those different directions that I was talking about just now. But the great thing about these standards is that they enable you to relate the sort of less tangible aspects of the data. If I can make this slide change, there we go. So you can start to use quite verbal and almost philosophical terms to describe numbers or pieces of information. So you can talk about organisations and people, you can talk about assumptions, objectives, targets, what are we trying to achieve, what state is something in, how are we measuring it, what is that asset, and the links that go between those different pieces of information. So you can really start to describe some quite complex data in some very consistent and coherent ways. But it starts to look quite complicated quite quickly. The key benefits of this are that, for example, with our real-time infrastructure monitoring, we can hopefully produce systems that are safe and save lives, keep our infrastructure operating efficiently. We need a smart framework to correlate all that very, very very varied sensor data that I mentioned before to enable better engineering understanding. And we also need to coordinate information that's coming from a lot of different organisations, and I'll talk about that in just a moment, and improve the communication between the different agencies. And these smart city standards are really endeavouring, particularly with those last two, to tackle that organisational barrier. So just to sort of elucidate this a little bit with a real example, I don't know how many of you go through London Bridge Station ever, but if you have recently, you'll know that they're completely rebuilding it while keeping it operational. So it's still taking 500,000 passenger journeys a week, and bits of it are in this state. So we've had the great opportunity to go in and do all sorts of exciting things there, measuring lots of different things. And I'm going to talk about just one of those exciting things, which is a particular arch. Oh, the other thing to say is that we've got high-risk construction activity, which is the bit we're interested in. Above some of these arches, we have active rail platforms. So we've got rails running above them and people walking around. Below this arch, we've got the Jubilee line, and a number of both important lifelines. So we've got critical infrastructure passing through the station, and we've got the Shard above the station, and we've got 2 or 3 hospitals around the station. So it's a very complex environment. We're not building in the middle of a green field here. So this structure that we've been measuring, among other things, it's quite old. It was built in 1893. We know a bit about it, but not much. It supports the running railway. It's built in a range of different soil types, and it's ultimately going to be demolished. But before it's demolished, because of the construction cycle, they wanted to drive the piles for the building that those piles are going to support whilst that arch was still there and whilst it was still supporting the railway. When they started this work, the arch wasn't cracked and there didn't seem to be any water drainage problems. So we had quite a good situation to be looking at. But in order to understand this arch, we needed to deploy a whole range of different sensors. And they were coming from a whole range of different sources. So the key question we want to answer at a given moment in time is this arch still safe to carry this railway? And is this piling operation badly affecting either the arch or the Jubilee line tube line underneath? Because lots of people would be very unhappy if either of those things went wrong. So Costain, which is a big construction company, are gathering survey data from the arches and the tunnels, and most of that is point data taken maybe once a day, maybe a few times a day. We've got rail track displacement data from Network Rail, so they're looking at the rails running along the top of this arch, and they're mainly looking at sort of angular data. We had fibre optics and wireless sensors in there, so our fibre optics data was draped over the arch and measuring the shape of the arch. And we were also looking at laser scan data, which we were gathering every few days. And then we had some design predictions. All of this data is about one location, which is experiencing one process. How do we glue it all together to better manage that construction process and improve the communication between all these different organisations that each has a different bit of the information? And by the way, that was quite a coordinated set of people. It could have been much worse. The data also exists in different formats. So that's the laser scan data. We've got some point data from Costain. We had some fibre optics data that we were gathering, et cetera, et cetera. And the problem is that the raw data is actually not at all useful, as was said earlier. Raw data doesn't tell you very much very quickly. You've got to be able to interpret it. So how can you evaluate the data? How can you, for example, decide what trigger levels to set? When do you set those trigger levels, et cetera? And what kinds of questions do you want to ask of the data? Now, in the operational phase, you probably want to ask some questions that are relatively easy sometimes to get at. So, for example, have we got a crack bigger than 5 millimetres in this arch yet? And if you have, trigger an alarm and we'll stop and think about what we're doing. So if you can glue all of that data together simultaneously and track the physical condition of the arch, then you can make sure that things stay reasonably safe. But you're going to do another piling operation. So you might want to say, so in this arch here, where I've been doing these 3 piles, how many black alarms were triggered? Did we trigger any black alarms? And if we did, what were we doing at the time? And how should we therefore modify our process so that that doesn't happen in the next piling that we're doing under the next arch? Oh, that wasn't the one I wanted to come to next. Another question might be, how do we get good quality data? So actually, how many strain readings do we need? How many data readings do we need in a strain profile within a particular tolerance to get the sort of data that we need? Because that might change how we gather our data going forwards. How does the choice of analysis equipment that we use to gather that data affect the quality of the readings? And that might be quite a long-term question, because we might go back to look at the data in the future and say, well, actually, we know that what we were doing then with that data was a little bit flaky, so we'll reanalyze it, and then we've got better data going forward. And if you've got an asset that you're looking after for 100 or more years, that might be an important thing to do. And then the final one might be, so what's the maximum strain observed during a particular process? Because actually we want to influence the design codes of, for example, a particular kind of tunnel, and we're doing some work on this at the moment, so that we can use less material in the future. So you've got a whole range of different questions that you might want to go back and ask. And actually, conventionally, you might need to structure your database in quite different ways to access this data most easily. So that's one of our challenges. So the big challenge at the moment is that the semantic tools that primarily focus on the thematic relationships, which are some of the relationships that we just talked about, are very good at connecting those thematic things, but they're not very good at doing spatio-temporal relationships, which obviously is also very important in our sort of context. The GIS and spatial database technology that exists does spatio-temporal stuff really well, but doesn't do that thematic stuff very well. So when we want to start to ask questions that cut through the data in a different direction, they're challenged. So why don't these kind of conventional relational databases work? Well, you've got an example here where, for example, you're measuring displacement in the top axis, but temperature might be important as well. So, for example, if you're measuring on the sunny side of a bridge, the strain changes with temperature as well as with anything kind of physical going on. If you want to start to add temperature data into that, you could add columns, but if the temperature is being measured at a different frequency to the strain, then you can't do that, so you have to add another row, and you have a whole load of empty cells in your data sheet. In order to gather both your sensor data, your displacement data and your thermal data at the same time. So you very quickly run into a situation where you've got quite an unwieldy data set that's very difficult to query, and it's very difficult to add new variables and modify what you're doing with it. It very quickly gets very clunky. So one way to tackle that is to create triples, which enable you to measure a number of different things. And again, this is data scientists, so I apologize if I'm destroying your field here. But the challenge with triples is that it's very difficult to sort out time with that. And you're measuring, if you're varying time but not location, for example, and not, in this case, we're measuring air pollution in Bristol, the pollutant we're measuring isn't changing, and where we're measuring it isn't changing. So we're gathering a whole bunch of redundant information every time we gather a data point. So again, you're starting to get quite unwieldy groups of data. So another way to, and when you start to look back at your original data map, which we could use, again, to do this, if you have to gather all of that information for every time slice, again, you've got a lot of redundancy in what you're gathering. So what my data science colleagues are starting to explore is, can we use graph processing to look at this? Now, graph processing is quite different to the semantic web stuff, but if you use property graphs like this, then you can start to store key value pairs on each of the edges and each of the vertices of your relationship here. And that means that the way I describe this in my very simplistic way is that for each of those blobs or each of those lines, you can just hang the key value pair off that you want. So instead of repeating all the data about that blob every time, you're only capturing the bits that change. The other challenge that we have is that quite a lot of the time we want to use this data to monitor a live process, be that a construction process or operating our infrastructure. Typically, to do that, if you've got lots of data coming in, you have to do that in memory. So to get real-time predictions, you're working in memory, and you're using features and correlations that already exist so that you can work on a sort of a smaller batch of data and churn through it. However, the whole point of this is that we're just beginning to be able to measure this stuff, so we're evolving our understanding all the time of what this data means and what data we should be gathering and so forth. Now, to do that well, you need to be looking at what's called the map-reduce approach and doing batch processing, but batch processing happens offline. You use a larger set of data, you extract different features, you develop new algorithms and new correlations. For us, what we want to be able to do is do both of those two things simultaneously. And at the moment, we haven't found, or we aren't aware of a good way of addressing this challenge. So one of the big questions for us is, how can we run that in-memory real-time prediction process and have it feeding into and feeding from the map-reduce process continuously, so that we're not having to stop and restart things all the time? So just to kind of come back to the summary, really, in our world, we have a lot of different types of sensor which are generating very different kinds of data, and I know we've heard a few examples today of other people doing that at very different time intervals, anything from several times a second to once a year. And we're using it for a number of very different processes, and we're probably using the same data for a number of different processes. So there's the immediate, the design code modification stuff, and the long-term asset management. And current approaches tend to handle either the thematic linkage very well or the spatiotemporal linkage very well, but don't address both of those very well. So in the future, what we're hoping to do is, working with this sort of graph data approach, apply some machine learning algorithms, such as deep learning techniques, to extract the features and correlations, and then, as I said, develop this way of doing real-time prediction on infrastructure behaviour based on those statistical correlations and relationships and having them feeding into each other. In order to, and this is our centre's tagline, transform the future of infrastructure through smarter information.